No? Everything is crystal clear? Yeah? I say I'm doing stuff that sort of that I think is relevant. Hopefully it is to you. Otherwise, your questions can be, hey, I want to go in this direction. You can ask me anything you like, and I will happily admit I don't know it, or else I'll tell you. Okay? So somebody asked me to talk about scope today, and I will. Okay? So how R finds variables. And I'm going to tie it together with something that is going to be, this is tricky, okay? And if you don't understand all of this, just take away the big picture message. Remember I talked about non-standard evaluation and tidyverse and all that sort of stuff? Well, here's an example of some interesting stuff that's going to show about how to debug some of these things and try to understand. This is a very simple, why are we echoing so much?
I don't know. Can you get your
I can. That would be better. Thank you. I don't want to hear myself. So as usual, here's the website. Here's the site with some material. I tried to write a long narrative about what we're going to do, but just work with me here before you go reading through it, and because it's actually, again, a big part of debugging is actually trying to figure out what questions to ask to rule out certain problems and actually identify which are more likely solutions or places to look. Okay, so what did I do? I haven't actually filled in all of the links in this thing yet. You can take a look at this, and we'll talk about this in two different ways. So just look at, if we're looking at boost.md. How many of you know about the statistical concept of boosting? Okay, good. Doesn't matter. Okay, it's not that important as to what we're actually. Hang on a second. I will be back. I like just walking off for dramatic effect. It's like you don't know if I'm coming back. So this is a nice statistical concept. It's kind of fun. So what we're going to do is we're going to look at data. Okay, and again, don't worry about the details. This is about actually programming, but we have to have something to program. Okay, so you have a model you have a data set that looks like this. This is X and this is Y, and we're going to fit a linear model to it, and you'll get the best fit. Okay, there's a nice trick that you can actually do for classification or regression, which is, and it's got pros and cons like all methods. Okay, what we're actually going to do is, we're going to do the following. We're going to do a fit. We're going to fit a line to this data. Okay, X against Y, or Y against X, you say, Y against X, and then what we're going to do is this thing. We're going to find out that we get a residual here. We got this is a big residual. This is a reasonably big residual. This is very small as the residuals go. So what I'm going to actually do is I'm going to do another regression. Same data. Okay, exactly the same data set. But what I'm actually going to do is I'm going to take this observation, which has a residual from here, and I'm going to increase its weight. Okay? I'm going to do weighted least squares by favoring the observations that I got most wrong in the previous fit. Is this clear? And then I do it again. So and I always look at the previous one and say, so in this case, I say, well, I got this one pretty close. It gets less weight, which is exactly counterintuitive, by the way. This one gets more weight, which is exactly counterintuitive. So, but then I go fit this line, and I get a different line. This time I'm going to get this line. Now there's a magic piece of, okay, we keep doing this until we get bored. There's a point at which actually it turns out that this is a very bad idea to keep going, but nevertheless, we do it. Let's suppose we have capital B of these. Okay, we have B different fits. Now, and I am playing really loose with the truth here, okay? Just because you only need to worry about the basic idea. What we're going to do is, this fit is not as good as this fit, okay? Because it's chasing after the hard to fit observations, but this does tell me something. Okay, so what I'm going to do when I'm now going to make a prediction on a new value, So I get a new X star, and I'm going to make a prediction. I'm going to predict Y from this one, from this one, from this one, from this one. And I'm going to actually, so this, I'm going to call this fit 1, fit 2, all the way down to fit B. And what I'm going to do is I'm going to say f of I X star. I'm going to predict on that guy, but I'm going to use weights. And that's going to give me my real prediction for X star. Okay, what I'm going to do is I'm going to take a weighted average of the predictions from each of these, and I'm going to lower the weight on this one relative to this one. Okay, so I increased the weight on the residual here that was biggest, but I actually I don't give this guy as much credibility as this model. It's a very nice idea. Okay, this is called boosting. Okay, so we are fitting multiple models. We've actually, our model is to have multiple models. This is what's called an ensemble. Okay, and this comes up in random forests and boosting and different things. We actually combine multiple models in this way. We chase after the hard to predict ones, then we fit multiple models, but then we actually weight the predictions from each model. Everyone with me? So it's easy to program. Yes? So here's what we're going to do, and you can play along if you'd like. Okay, the code is sitting in this. The code is, I believe, sitting in this this file. Okay, and of course I'm going to do it my way. And there, oh, stop it. Okay, and as I say, there is a reason why we do. There's a reason why I am doing this, and it's got, and there's hopefully it will bring up several different issues. Okay, so the first thing I'm going to do is I'm going to run this on a very small data set because there's no reason to run on a big data set or anything like that. It's just the empty cars data that I love all the time. It's got 32 observations. This is going to be very fast. So here's actually what we do, okay, just to actually show you the mechanics of this. What I'm going to do is I'm actually going to start off with I am going to start off by setting my weights to be 1 for everything, okay, or 1 over n. The good news about the LM function is if you give it weights, it'll normalize them for you, so we don't have to worry about dividing by n. So every observation here gets a weight of 1. So I've just said, hey, the weights are 1 for all of the observations. Everyone with me? If there's any questions, yell, because it's going to get uglier after this. Okay. And we'll start thinking. Okay, so what do? This is what we do. We fit the first one, so that's the guy on the top left, and I'm picking any model I want. If you're not familiar with the LM function, this is R. Okay, LM is for fitting a linear model. This says miles per gallon is modeled as a function of cylinder and weight. So it's got 2 predictors, and we're predicting 1 response. Okay, everyone happy? We have to give it the data set in which it finds the observations, and there's an argument called weights, which actually does weighted least squares. In this case, it doesn't matter, the weights are all uniform, so, but given that we're going to be doing this in the next round, okay, and just for fun, because there's the very first residual. Let's just take a look at it, okay? That's fine. And now we change the weight. So this, by the way, this is the algorithm. Now we want to write a function to actually do this, okay? So I now just set, so this is not the formula, by the way, for boosting. I made it up. This is just the ad hoc, sort of the simplest thing to understand, so I don't have to explain any math as to why we're actually doing it a different way. Do not ever boost this way. It's not bad. It's not stupid, but it's not the right way to do this. Okay, we basically say, here's the weights. I take the absolute value of the residuals and I divide by the sum of the residuals. Okay, so I take the big residuals get bigger weights. The smaller residuals get smaller weights. Okay, that's fine. So there's the weights. They have changed from 1. Okay, and now I go down and I basically fit F2. Okay, there's F2. There's F1, by the way. You see the actual intercepts have changed, or the coefficients have changed. Everything's changed. We're actually getting 2 different fits, and how do I glue them back together again? That's the least of my worries at the moment. We're just going to actually do the boosting at this stage, okay? I'm not going to do the prediction. We can talk about that later on if you want. There's nice ways to actually organize your code to do the predictions, which I say, if somebody reminds me later on today, we will do that. But we're just fitting these things, and I want to get the answers back as here are the B fits. and I'll get some other piece of information, because remember, I need to weight them later on as to how well they fit. So I'll get the goodness of fit. I'm going to make stuff up and say, we'll just compute some of the residuals. The bigger that is, the smaller the weight we'll give them, because it's fitting less well. Okay, so get the idea? What I've done is I've done this manually, one step at a time. We need to do this for maybe 100 iterations. That's when I stop doing it manually. Okay, I want a function to do this. It should, I hope, and please talk to me if you want. Okay, there's the second residual. Okay, if we actually just, remember my, and again, this is actually a useful thing to do, okay? That is a plot of the residuals from the first against the second fit, and this is useful. This says they are not the same fit. They are actually different residuals, otherwise they would lie along a straight line. So it's a good error. Visualization is a great debugging tool just to check, did it give me what I expect, okay? So when you're in a programming language like C or Python or Java or something like that, we don't have data analytic tools, whereas when you're in R and you're writing code, you can actually look at the results and actually start doing descriptive statistics to actually check, are they same? Okay, life is good. Okay, so we'll repeat this. Here's a function that I quickly wrote. Okay, it takes the model, because we need this to work for different models. It takes the data set, because we're trying to make this general, okay? So it takes the model and the data, and it takes the number of steps, or I could have called it capital B, but steps is good name for this, and I leave it at 5 as a default value. There's no good sensible default for the data. Perhaps I could actually say the model is y tilde dot. It means just predict y, but there has to be a variable named y, so that doesn't make sense. So you have to specify both of these for writing for calling this function, but this we'll just leave at 5 for the moment. And now I allocate the vector. I allocate a list to hold each of the fits. Remember, these are not numbers; these are actually full linear model objects. So I need a list to combine them. I pre-allocate this. My goodness of fit is going to be just a numeric vector. Okay, that's going to be the weights that I give to each model later on. Okay, and then my weights I start. So all I've done is I've actually shown you how to manually do this. So all I do is I just copy my code one line at a time in, and then I sort of say now generalize it. So I say for I in 1 through steps. Okay, steps better not be 0. I should probably check that. I should write this more carefully, but who in the world actually do this 0 times? Okay, and I stick the answer into Lm. By the way, I seem to be actually contradicting what I talked about last time, don't I? Except for this time it's real. Okay, I cannot actually do this with an lapply, because the ith iteration depends on the previous fit. So I can't do these in an lapply. Okay, I need the value of the previous fit's residuals to actually change the weights. Okay, so I actually have to do it with a loop. This is one of those annoying cases where you go, okay, that's fine. But at least I pre-allocated the answer. Okay, so I compute the residuals just like I did. I compute the absolute value divided by the sum to get the new weights. The weights will now get, this weights is updated, so when I go through it again, we're done the weights. Everyone happy? This is like shooting fish in a barrel, okay? This is yes?
I was wondering, why are there 2 equal signs on ANS?
ANS, answer?
Yeah.
Because what I've actually done is I'm lazy. And good that you noticed this, because it may or may not come back to haunt us. Or not. I don't know. Not giving nothing away, okay? This is basically saying, compute this, assign it to fit, and then assign that value, which is also this value, to this guy, because I want to keep this, but I don't want to keep on typing ants double square bracket I. Okay, I'm lazy. Okay, because I'm going to refer to fit down here. It's the way I wrote the code, and I did. So I cut and paste these things in, so I was making minimal changes. I could have easily written fit equals this, then ants equals fit, and then move on. Or I could have just said drop the fit and put this guy in here, but I'd already cut and pasted this in. So, and you do this, and then you go back and you edit it. But, and this is how errors get into code. Okay, is that you just cut and paste, and you forget that you did that, and all of a sudden bad news is happening. Okay? That is okay, and then we compute the goodness of fit, which is the sum of the residual squared. Okay, and again, I'm making all this stuff up. Okay, do not use this as a statistical approach. Okay, don't say I ever did this. Okay, so okay, it's just to get the point across. And then what I do is I create a list that which contains the fits and the goodness of fit statistics, and that's going to be enough for me to actually make predictions later on. Okay, but I have to write another function to do that, but that should live in a totally different function because we're not predicting anything at this stage. All we're doing is just essentially fitting the boosted model. Everyone with me? Simple. Does it work? What's the first thing I should do now that I've written a function? Remember I told you we kind of did this interactively and then I cut and paste the code in. So what's the very first thing I should do?
Source it.
Source it, that's always a good idea. Okay, I should source it. Okay, we'll source it then. Okay, fair enough. Okay, I should source it. Okay, so let's source that in. I forgot about that. That goes without saying. Okay, boost.r, okay. I believe, yeah, that's in boost.r. I hope I haven't changed that one. So let's just take a quick look at boost. Okay, so what's the next thing I should do? After having defined the function and checked that it is actually there and it looks approximately like I said, what's the next thing I do?
Check the global variable.
Check the global variables. I didn't do this first, but I should have, but I didn't. Okay, when I wrote this, find globals in code tools, just let's eliminate the possibility that I put in global variables because, okay, find globals of boost. Okay, I don't want that. I want to split the functions and the variables. It says there's no global variables. Here are the functions that you used. These all look legitimate, so that I'm not missing anything. Okay, but the good news is I don't have any global variables. And we typically are interested in global variables rather than global functions because we need global functions. So this all looks good. So what do I do now? What do I do now? I've written a function. It's got no global variables. Take the rest of the day off. Now I need a test case. Now I need to test it because it ain't going to work. First time you write code, it should not work, okay? Because you're going to make some stupid typo. So the source probably will fail because you got a syntax error, okay? And then you got to figure out where the syntax error is, and hopefully R tells you. But I wrote this code, and magically, in some way, when I was editing a whole lot of stuff, I managed to put a tick in the code, and it said I can't source it, and I couldn't find the tick because it was just a single little tick mark. Okay, and eventually, this is annoying. So we do this. Okay, how am I going to test this? I'll give you a hint. We're going to call it. Okay. So it takes a model and it takes the data. We might as well use the same data on the same model. So it's MPG is cylinder plus weight against MT cars. And I'll just run it through 5 times because I don't really care. And I'm going to assign this to some variable that I don't care about. And it works. So we're done. Now you can go home. Okay. So what's the next step? Check the results. How do I check the results? I can just print the whole thing. I can do that if you'd like, but and fortunately enough, there's not too much going on, so we can print the whole thing. So, happy? I mean, printing the results doesn't actually check it's correct. It just prints the results. Now I got to interpret the results. Are these correct? Because if they are, then we have to check, give a few more tests, but then we're happy that it seems to be doing the right thing on a couple of inputs, and we go home. The what? Pardon? Well, the model shouldn't change. The model formula is exactly the same. The coefficients don't change. Okay, and the goodness of fit doesn't change. Nothing changes. Okay. That's fine. Is it? We actually know this. We know that it's wrong because we actually did it by hand for 2 steps, and we can check that this code is not doing what I did by hand. So now what do? We debug. Go for it. This code is on on GitHub, on that address. You can just source that URL in for the boost.r. Okay, I told you how to debug using the debug function. I think I mentioned trace today. Okay, so you could trace when something is getting called. You can do all sorts of fun stuff with trace. Okay, talk to people around you and just figure out what is your strategy for debugging here. Okay, and I'm serious. Just take 5 minutes to see where you're going to go and debug this. Do not read what I have written. That's cheating. Okay, and I will know. Does anyone know the answer? Does anyone think they know what the problem is? Good. And debugging is really hard. You have to come up, you have to figure out how you're going to get a strategy to find information that you want. What are you trying? I was wondering. I thought you'd abandoned it. I think that's good. I'm glad its owner came back. I thought it was yours. I don't see a lot of debugging going on.
My scribe is looking at the data.
I don't get to work if you don't get to work. Well, I told you that because it's in the scope directory.
That's in this function. Well, no. Scoping basically means like what variables are available. Duncan's gonna explain this one.
It's where scoping means where does R find the variables, and I have gone through standard evaluation and how R works, so we know everything.
I didn't even see how you got the boost function to work, like what you put in as
I will show you. So I will.
Yeah.
There we go. So it's just boost with the model that we used before, and then the empty cars, and then so you give it a data set, and then the steps just defaults to 5. If you want to save valuable milliseconds, you can just do 2 steps. it won't matter. Time's a ticking. Nobody wins the $1 million prize unless you come up with 2.
No, I know, but I think
Well, Ben, what did you do to it? Oh, come on.
object wait, it's not found.
Oh, you didn't do what I did. I told you play along. So that actually is very, very helpful. You're very lucky because, okay. So to leap ahead, to give you, so here's a trick. If something doesn't work, so when you're at home and you're Wi-Fi router, your cable modem, or whatever it is that you're using to connect to the world, what happens when you don't have internet? What do? You turn it off. Okay. And you turn it back on, and you know, okay? So the equivalent in R is to quit out of R. Okay, so I mean, you've just seen what I've done here. Okay, where was it? I ran this, and it runs, and trust me, it runs. Okay, it's absolutely fine. So okay, but we got the wrong answer. So and somebody had a problem where we were installing packages on Monday, and then it didn't behave itself, and I ran R, not RStudio, and it behaved itself. I was like, oh yeah, okay, fine. We did all sorts of stuff, and then we said, let's quit out of RStudio and then go back, and all of a sudden it works. Okay, good idea. Okay, so now, hopefully this will just behave itself, and that anomaly that we get, but that's not what actually happens. Okay, that's not what happens. We actually get an error this time we run, which is hugely valuable, because otherwise we could have been here for hours. Okay, but at least this actually, so we're lucky to get an error.
It said we took the how you define weights within the function.
So the good news is I could have thought that actually weights was a global variable, and now it's not there. But we checked for there was no global variables. And if we actually take a look here, and again, hopefully, so weights is actually defined there, and it's not used beforehand. So it is a global. It's not a global variable. That's what the find globals told us to. So we'd already done due diligence here and actually done the right checking. So it's there. So why on earth can't this find weights? Okay. So the reason it worked for me, apparently, because I did tell you, play along with me. Because what did we actually do? We did this. This is what I did to do it in the past. Okay, and this is a much more fun game. Okay, it makes it's a much harder game. So this is what I did. Remember, I said I went through this manually, and I then fit F2, and then I checked everything. Okay, and now let me run my boost function again. Okay, now it behaves itself, but I get the same answer for each fit. Now I got two pieces of information. I'm lucky, so I quit out of R, start up again, run boost. It didn't work. So now I got two pieces of information. When I've done it manually, and this is hard, by the way. I'm hesitant to actually walk you through this, because I'd love to leave you here for 2 hours, seeing if you can figure it out. Okay, because debugging is easy when you watch someone else who knows the answer debug. It's like, well, I would have got that. Well, of course I would have got that. It's easy. And then 3 hours or 3 days later, you go like, it looked so easy on that problem. Okay, my problem must be infinitely harder. No, there really is a skill to debugging. Okay, and it's an enormous amount of experience. Okay, unfortunately. So, but it really seriously helps debug if you can understand the computational model that's going on, and that's part of the problem with non-standard evaluation. You can't, and you have to reason about two different things and so forth. But it's nice you sort of you have to generate evidence that can rule out certain hypotheses or certain conjectures as to why something's working or not. So we've got two pieces of information. If you were a crime detective, you would write them down on a board, and we would actually try to figure them out. Okay, and try to sort of figure out where to go next. So where will we go next? What's the next? What's your next approach? We were lucky so you were lucky because there was somebody in the room who didn't play along with me and said, I'm not doing the manual parts, I'm just going to jump in halfway through, and then we got that extra piece of information. So you can be that other person by just starting another R session or whatever, or go talk to somebody else.
I guess maybe manually check each step what's the weights.
So where would we okay, tell me specifically what weights you want to check. Where? In which?
WPS.
Okay, so you want to debug the boost function. And so, okay, we talked about the debug function. So let's do this, okay? Boost. Okay, so that's okay. I'm debugging boost, which means I'm going to stop every time I'm in boost. I'm only going to call it once. I'm just going to stop once, and then I get to control what happens next when we evaluate the next step. Okay, so now I go back over and I run this, and now again, if you have any questions, this is the stuff that unfortunately isn't in books. It tells you how to run the debugger. It doesn't tell you how to think. Okay, because every problem is different. But this one's fun. Okay, but you have to get experience. So we're now sitting there. You're sitting right here. It's about to run the first expression, but we're in control. So I say next, please, and it says sure. And then I say next, and then I say, okay, where are you? Well, we've got the ants defined, we've got the data model and steps which come from the parameters, so I can look around. There's nothing to look at here. We haven't got to weights yet. Now I've got weights. Happy? Everyone happy? It's what we expect. There's no point, there is a point. It's much better when you're debugging if you know what you anticipate. So then you can confirm that it is what you get. Okay, the second you find something that you don't expect, you've got two decisions to make, okay, or one decision to make about what the possible cause is. Either it's wrong or your expectations were wrong, okay, and you don't know which one it is. And you sometimes go like, I'm convinced it should be this, but you're actually wrong. That's fine. So we go next, please, and now we're into the loop, okay? So I go through this, go through this, go through this. I'm just about to execute this command, so I now I've done it. So here's weights. Different? Don't look the same, do they? Okay, I bet you if I look at if I look at the residuals of fit and I look at the first one, that should be the same as the one I had when I did it manually, because nothing's random here, by the way. Okay, everyone happy? So let's go again. We're going round again. Run the weights. Are they the same? It's hard to tell, isn't it? Okay, so this is why I kind of just printed one of them. So that's the current weight. Okay, and then if we go back up here, I think I got rid of it, so we can go round again. So let's look at weights 1. Are they changing? Oh, 6048, 60477. So they are different. So this is actually changing the weights. Okay, any other bright ideas? No, I'm just kidding. Okay, so it looks like it's right, which is more evidence yet again. Okay, the good news is that if you do enough intelligently here, you will eventually start eliminating all the innocent victims, okay, who are sort of chastised. So it doesn't appear to be boosts calculations of the weights. So any other suggestions? That was a very good suggestion. This is a really good place to start. It's your code that's broken. It's always your code that's broken, okay? Because the other code has been attacked by hundreds and hundreds of thousands of people, probably millions of times, okay? So it's unlikely that code is wrong, but possible, but it's nearly always your code. We wrote this quickly. It's my code. So next, what do we do next to uncover this puzzle? By the way, would anyone have written this code differently? So Michaela, who likes to simulate, and would have gone off and simulated this and written the code this way and then showed that boosting has no variability whatsoever. I'm just kidding. Okay, you all would have done this if you were simulating, or if you were actually fitting a model and publishing papers. You go, look, it's great, here are my predictions, and they would be wrong, okay? And this is a really serious problem, okay, because it worked. We were lucky in some cases that it actually didn't work, and we got an error, okay, but we got the wrong answer, which is really sad, and we sometimes don't check, and sometimes it's not going to be so simple to see the wrong answer that they're all the same. They might be wrong in a slightly odd way. So what am I going to do next?
Something wrong with the return
Of
like return this equal answer.
Well, let's go and take a look. So we can take a look at that. I mean, now that's a hard one to check. I mean, we can go look and look. It's not so much, I mean, this is a very simple command. It just says, take the value of answer, put it into a list, with a name fits. So let's look at ants, okay? Or let's look at GOF is even simpler, okay? So we haven't filled in, we have only gone through 3 iterations. So GOF is actually, they're all the same. And I guarantee you that ants has got only 3 elements that aren't null, and those 3 elements are identical. Okay, and you know, and this is another good thing I can say is I can say identical of fits of ants 1 and ants 2. It says they really are identical. So it's not the return that's happening. No, they genuinely are identical. Okay, anything else? Anyone else going to save us valuable amounts of time today? What do I do next? Just what do we do next? Yep.
WGS is a vector.
It's a vector, yes.
But when you assign to it, you assign this you don't assign it with an index.
No, because I'm actually replacing weights with a new vector of weights. I'm saying weights is all ones now. Compute a vector, and there's the residuals will have as many observations as there are in the data frame. So this will be a new vector, and it just replacing the whole thing. It's weights. We saw that. I mean, we can actually walk through and see the weights we saw with the vector. What's my next trick? I only have 2 tricks, so we got one trick which is debugging, and the other one is thinking. And thinking is hard, so we always go with the debugger. Okay? Although we try to actually think a little bit ahead of time to make sure we're not just wasting our time with debugging, and we try to debug the right thing. Yep.
I was thinking about writing a function instead of writing the part.
That was our problem. We wrote a function. You're kind of trying to double down?
Yes, that chunk. So you can, because I don't understand the error, but I think that it's not passing down correctly to the LM.
Okay, so I don't want to write a function to check your hypothesis. Your hypothesis is it's not passing the arguments to LM correctly. So I want to go after that one. Let's actually ask LM what it got for weights and see, was there somehow that when it threw it over the wall into LM, did somebody actually start getting the wrong thing? So now what I can do is I can quit out of this. I will undebug boost, because I don't boost even. Okay, and now I will debug LM. We can debug both of them, but I just don't want to be stuck in both. Okay, I'll debug LM. So we should get 5 calls to LM. Okay, is equal to this guy. Okay, I'm going to run. Here we are. We're stopping now in LM. I can say, what's LS? Now, what would you like me to do next? This is a great idea. Something is going wrong with the weights. By the time LM sees them or is utilizing them, something's going wrong. Check the weights. It's an argument, so we don't have to run through the code at this point. Weights. Okay, happy? That they look correct. So I'm going to continue on, because you didn't ask me to not continue on. I'll just continue on. We'll check the weights. They're the weights. Continue on. Okay, are those the same? Let's look at the last ones here. I'll compare. What happens? Where am I? Where am I? Are these the same? Are these the same? So the first ones were 1s. The second ones down here are the same as the third one. So it worked for the first 2, and it failed for the third. Are we any the wiser? And by the way, again, I have 2 inclinations. One is to just tell you the answer and move on, so we don't belabor this. The other one is not to tell you the answer and make you and not let you leave here until you solve it. It's such a nice problem at the same time, and you may think this is totally esoteric. The answer is, I'll give you a hint here. The answer is non-standard evaluation, and there's a reason I'm showing you this. Is it is extraordinarily nasty. Okay, it's in LM. It's one of the workhorses of statistical modeling. Okay, and yet something as trivial as this goes wrong. Okay, most of the time you're just interactively calling LM, and life just behaves itself, and it does behave itself in this case because I showed you that, because I manually ran through this code, and and it did the right thing. So there's a problem when you go to a function and it behaves differently, and there's a very rich reason why it does it. That's very clever, but it's very confusing. Okay, so what am I going to actually do next here? By the way, I'm gonna cheat here to move things along. I'm going to go back out here, and essentially I'm going to start this R session from scratch. I happen to know what the answer is, so I'm just going to actually just not bother starting the R session from scratch, but change the one bit that is important. Okay, I'm going to remove the weights. Okay, if I'd actually looked at the weights, well, actually, you know, I shouldn't have done that. If I do this now, okay, let's just do this again, okay, which is see what I got here? I removed the weights. We back to this error message. Okay, yeah.
What kind of object is weights after you re-evaluate it?
When in the boost command, in the boost function,
Before like that.
it was just a vector. It keeps going around as a vector. Okay, so we looked at it. It prints out. It's a vector. Genuinely, it's just a It starts off as a vector of ones, then it becomes a vector of of real valued numbers. Okay, nothing changes. The only thing that changes is contents, and then they stop changing. Okay, when I do this, I get an error. Okay, let me just show you the LM function. And again, it's a pain. Nobody wants to read code, okay? Nobody wants to read the manual. Nobody wants to read code, okay? Because now you have to understand. Here we are. There's weights, for example. Where else does weights get called down here? So I'm going to see who's screwing with the weights. There, okay, it's used there. It says match of that guy into the names of MF, and MF is this weird thing called match.call. It's actually not very hard to understand, but okay. If you see anything that you'd like me to address in any way, let me know in this function. There's another one. It says create the model weights and assign. There's a word weights, model weights of MF. MF was this thing up above. W is here. Then it says weights must be a numeric vector if that's not true, and then it goes on. Okay, now we got to go and look for W because that's got the thing to do with weights. Okay, and W, and there's the weights in here. Okay, and now if that's not null, so there we go. It now uses lm.w fit for weighted least squares fit, and it's got the weights in there. Maybe that's where we should take a look. Okay, so I'll tell you this. If you actually go back and run this manually like I just did, okay, then if you do lm.w fit, okay, and you debug that and you look at the weights, you'll find out the weights are the same as the one in the global variable. Okay, the one that was actually I created manually the second time round, and they've got nothing to do with the weights being passed down through the LM function from the boost function. Okay, is this clear? How do we know this? Okay, so what we do now is RLM help. Okay, we start with the documentation. Okay, so it says there it is, weights. We go down and look. It's an optional vector of weights to be used in the fitting process. It should be null or a numeric vector. If non-null, then the weighted least squares is used with weights. That is minimizing bar. Okay. Okay, otherwise ordinary least squares, okay? Does that help you? So there's one thing in that, there's one bit here that is important. What's the bit that's important? See details. Whenever it says see details, it says see them, okay? Because there might be a detail. So you look through this, models for LM, nothing to do with weights. So we just do some pattern matching here to see for weights because we're not reading the whole thing. No weights, no weights, no weights, no weights. Weights, okay, non-null weights can be used to indicate the different observations have different variances with the values in weights being inversely proportional to the weights. Yeah, that's fine. Okay, or equivalently, when the elements of weights are positive integers that each response yi is mean of wi. Okay, this doesn't seem to help, does it? Okay, LM calls the lower level functions. Okay, so there's no information here, is there? Don't forget the small print. Okay. All of weights, subsets, and offsets are evaluated in the same way as variables in the formula. Remember the MPG is tilde cylinder plus weight? So we found cylinder and weight and MPG in the data frame, MT cars. And it says it will find weight, subset, and offset in the same way. That is, first in the data frame, but if not there, in the environment of the formula. And the formula was our MPG tilde cylinder plus weight. Who knew that formulas had an environment? Who knows what an environment is? Bummer, because this is all to do with scope. Okay, so you can do this if you'd like. That, we don't have to type it into the LM command. This is an actual R object, and we can say F equals this guy, and just now it's got a formula. And I can then pass it to LM, GLM, all these other functions, and I can compare the results without having to retype the model, the formula. Okay, this is great. Now, there's a really useful thing that S and S plus never had, these guys do, is that they have an environment. And the environment, you all know about environments because when you type search, or you look in your R Studio, it says here's the workspace. It's called the global environment. So an environment, I mentioned last time, is a container for variables, a name with a value. Okay, so they're just where we stick variables. Global environment is your workspace. So it had WTS, it has boost because we sourced things in there. It also has F now, and the environment of this guy is global environment. That's where we look for variables. Okay, remember what this guy said? All of weights are evaluated in the same way that we will look in the data frame for the variable named WTS, okay? Or in the formula, in the environment of the formula. The environment of the formula is the global environment. I had a WTS variable in there, so we found that one. And it was the same every single loop because we were always finding it in the wrong place. Wrong in the sense that not what we expected, right for what the actual code says it does. So this is truly weird. Now, how are you going to fix this problem? Okay, is anyone with me on this? Okay, this is non-standard evaluation. We went through the debugger and we actually eventually would have found it because we had to actually look through the LM code to see weights. We could have read the code and fully understood it, okay, but we did some pattern matching and said, okay, weights then gets assigned to W, W gets used in the lm.w fit. We could have actually debugged that and seen that the weights were not changing. Okay, and that would have clued us in, and then we would have said, okay, now what the heck is happening? And we could have actually slowly gone through. Okay, what's going on? How are we going to? So if you want, what we can actually do is I'm going to do weights is equal to rep of 1 of n row. I'll just put these back in again now. It doesn't matter what the values are. Okay, and now I'm going to call boost again, and call boost. Yeah. Okay, there we go. I get a different answer, but it's the same answer the whole way across because I've now got different weights. We're back in business here. If I want, what I can actually do is I'm going to debug LM. So I think we're already doing that. So now I just go back and I say, hello, come on, back up. So now I'm going to walk my way through here. Okay, there's W. We've computed W. There's W, all ones. Okay, I'm going to do this again. Did I get to, where am I? All ones. Proof that these are all the same, and that's why we're getting the answer. Okay, again, the debugger is helping us here. It helps if you actually know the answer so that you can actually check this is the spot. Now we've got to figure out what's going on. Oh, hang on a second. Let me just do this, which is undebug of LM. I'm going to remove the weights because I want to get an error this time, although it doesn't matter too much, which is, where am I? Boost. Anyone see anything funny going on there? This says, this, by the way, there's a really annoying thing that the debugger that I was using, and then this, I'm using another thing called recover, which is a different thing. So I said options error equals recover. It's always set in my R sessions because I'm always interested in debugging right there and then when I get an error. Okay, this is using the recover rather than debugger, and it prints the call stack backwards or upside down relative to debug. This says you started with boost. Okay, that called LM, we know that, we wrote that code. That called eval, and that called eval, and that called stats model.frame, and that called model.frame.default, and that called eval, and that's where the error occurred. So, okay, so you're actually seeing the call stack. This thing, that was us, then that was us again calling inside boost, and you see what's in effect. So we now can see everything. We can jump up and down these call stacks and go in and debug each one individually. I can just say, okay, let's go and take a look at number one. What do we have? This is my boost function. Let's take a look at the weights. They're all ones. This is boring because here weights is the same in the global variable as in my local variable. So, okay, but that's a coincidence. Okay, now I'm back. Anyone notice anything funny here? I'm talking about non-standard evaluation. Does anyone notice anything that seems to be occurring a lot? What's the one function that's being called a lot in this, the most often in this? Eval, and that's not a good thing. Okay, that is an ability for us to actually be able to evaluate in a totally different way. We're not following the rules that R has, we're actually evaluating a different expression. In fact, we've actually made this MF is actually, we've gone and said, construct a new call passing all the same arguments that you pass to LM to go and create this model.frame, okay? And then it goes off and it says, oh, I need to find the weights, and we behave differently than the way all arguments are evaluated because it's non-standard evaluation. Okay, so what it's doing is it's looking inside the formula. Okay, because if I actually go take a look here, and if I go down here, I say, where are we? Okay, that is the environment. If you recognize this is the MT cars data frame. Okay, this is actually, these are the variables. They're actually the columns of the data frame. Okay. Okay, and there's nothing there, so we're going to actually take a look, and you go like, okay, let's go here, let's look at the environment. Okay, it is a data frame here. This is this guy. Now, I'm not actually sure what's going to happen here, but let's just do this. Okay, and it's not happy because it's not a regular environment, it's a data frame. So we've got things. So now I don't even know where I can go and look. But if I look here, in the formula on the model, okay, if I look at this formula, we have the environment, which is the global environment, and that's where it's going to go and find the name WTS, okay, and you can't figure this out without reading the code, okay, and that's non-standard evaluation. And not only that, it's a lot of debugging, okay? So if nothing else, if you got nothing else out of this, it's a very useful thing to be able to just debug and go in and actually find out what's going on and sleuth your way through this. Any thoughts, questions? No? Everyone happy? Who knew this ahead of time? Okay.
Can she just first start conditioning for if WTS within the function, if the WTS does not exist, you create it?
In which function?
Within the boost function.
No, it does exist inside in the boost function. We defined it. It is there. It's just LM, or actually somebody else down here, is not finding it in the right spot because we're passing it down, and we said, LM, show me the value of the weights argument. And it said, it is what you gave me from the boost function. Then later on, it did non-standard evaluation to update the weight to actually compute W.
Can't you define that global variable within this function?
It's not, then it's not a global variable, but even if you do, it's not able to look back and find that because it doesn't know where. This is the scoping issue that we're going to try to actually get at now. This again, I've tried to set this up in that there's a message here. Non-standard evaluation can be incredibly complicated to understand, and it can give you erroneous results, not errors. Okay? And we use it in the LM function, which is really dangerous, okay? But now now we're trying to solve the problem. How do I solve this problem? I have two ways to solve this problem. Then I go home. Then I just go home. You really don't want to do that. I like it. I like the idea. So there is actually a design decision, and you could debate as to whether it was a good idea to do this. But in fact, there is a good reason for doing it. It's not stupid. Okay? For one is, so here's one of the problems we have, is when we actually wrote down something like this, when we said MPG equals cylinder tilde cylinder plus weight. Okay, suppose I didn't want weight. Suppose I actually wanted the log weight. Okay, this is a new variable, and I actually say log weight is equal to log of weight base 2 for some unknown reason. Okay, plus 10. And now many people would actually put this guy back into the data frame, into the MT cars data frame. I didn't want to, for some reason. I just don't want to actually pollute this data frame with an extra column. I don't want to put it in this extra column and then take it out later on. I'll just keep it as a separate variable out here. This has got as many rows as there are rows in my data frame, but I haven't defined my data frame here yet. So when I now do LM of this thing with my data, with my MT cars data, what I'm telling you is, and I showed you, this here is the same thing. Again, this is standard evaluation. I could have easily said F equals this thing and then passed F in. So F is essentially, F by formula is equal to MPG tilde cylinder plus weight. This is done at the R prompt. The environment I showed you of this is the global environment. Okay, great. Same thing here because it's just standard evaluation. We pass this down. It's as if we actually evaluated it. It is that we evaluated it at the prompt because we're doing this at prompt. Now, if we didn't do the right thing here with the formulas and the environments and look for things, if we didn't do this for weights, or if we didn't do the same thing as we do for weights, for this guy, I would not be able to find that variable. So everything would have to go into the data frame. That's not good. That's goofy. We want to be able to write large formulas here with variables that come from different places. So we grab the environment of this formula and we look there. We look in the data, and if it's not in the data, then we assume it must be in the environment, and if it's not in the environment, it must be along the parent of this environment and the parent of that environment, and so forth. And remember, and just in case you don't know, so here is, so that was F, the environment, and again, this is important for scoping issue. This is not just non-standard evaluation. The environment of F is the global environment. The parent environment of that guy is the stats package. And if you happen to look at the search path, that's the stats package. And if you happen to look at the parent environment of this thing, it will be that guy, and so forth. So what's going to happen is when we're looking for the log weight, it will look in the data frame. It will look in the data frame. It won't find it, and then it will look in the environment here, which is the global environment. Then it'll go to the next parent environment, which is the stats package, and so forth and so forth. And it will find things the way we expect them to find if we were doing regular computations. This is great. Okay? So that's a good thing. It's just we're also using it to find the weights. And that is good and it's bad. Okay? Because now we actually are looking, because remember when we did this, we said MPG, cylinder plus weight, MT cars. And then we actually said weights equals WTS. That's what we said in both the function and I think what it says is do not go and find this in the usual way. Grab the name and we're going to go look for it somewhere else. Okay, and we know where it's going to look for it. It's going to look for it in here, and then it's going to look in the environment of here, and its parent environment, and so on and so forth. If I'd wanted to, I could have said pi, okay, and it would have gone through and found it in the base Okay, it wouldn't have actually gone and grabbed it, but that's going to be a very different ballgame. But that's what's actually happening here, and this is what scoping is all about. Okay, what I mentioned on Monday was these guys, these formulas have environments. Does anyone know anything else that has an environment, that actually has its own environment? Functions have their own environment, and that's what makes the whole thing logical. Okay, is that we can use exactly the same scoping rules. Because if I have a little function like boost, for example, it says, okay, there we go. That's bytecode. That's not what I'm looking for. We can say, what's the environment of boost? Okay, and it says it's the global environment. So when I look at boost, it says, okay, we call boost, we get a call frame. Okay, so this is technical but not terribly hard. Okay, remember what I said? We call boost. We call boost. It opens a call frame, and it puts in model, and it puts in data, and it puts in steps. This is a call frame for this one call to boost. And then we sort of said MPG tilde, the formula, and then we said MT cars, and then we said this matches this matches that, because there's no named arguments here, so we've matched this up. Steps equals 5 was the default, so it's just sitting there. We haven't evaluated any of this because we're using lazy evaluation. Now we start evaluating this, and it says, hello, I'd like you to find the vector function. That's the first thing I need to do, is find the vector function. Actually, it's find equals, but let's just focus on vector because that's a little bit weird. Okay. Well, the vector function is most certainly not in here. So where does it look? So this is the call frame. So when we call vector, it will create another call frame for vector. But before that, I have to find vector. Okay, so these are the call frames. These are the search frames. They go in different directions. This is going to be the environment of boost. Okay, and that's the global environment. And its parent is going to be the stats package, and its parent is going to be the graphics package, and the next one's going to be the GR device packages, and so forth. Eventually we get to base, and that's the way it finds vector, and it comes back and says, now I'm ready to open the call frame for vector. So every function every function has an environment. We find when we're looking for something, we look in the call frame, the specific individual call to this function. We don't find the vector, and then we start walking along the environment chain. Okay? When we're down inside in here, and this vector, and this is the vector thing, and suppose it's trying to find the word data, it never looks up this way. It only looks this way. Okay? So it looks inside its own call frame, then it looks inside its parent, and so forth. And when we get down to vector, by the way, vector is actually in base. Okay? So this doesn't actually have any parents. That's the end. Okay? And when we get down into, let's suppose this guy ended up calling LM. So now we get a call to the LM, and this is in stats. So this is in the stats package. We managed to we found the LM package. Okay? Sorry, we found the LM function in stats. We made a call frame. Okay? And now, what's the environment, the parent environment of the LM function? Anyone know? Anyone know how to find out?
Stats is the environment that it's in.
It's in the package stats?
In the parent would be the next one up.
No. They're always trick questions. So this is actually where we go back to writing packages, and the fact that the package imports certain other packages. If the LM function, if the environment was to look along the search path, it would behave differently from me than for you, because it would all depend on what other packages I'd loaded. Okay, and in the order in which I loaded. Whereas if I say this, what is the environment of this? Okay, it's the stats package. So what's the parent environment for this guy? Okay, oh, why can't I type? Okay, that's the import of stats, okay, but not stats itself. Okay, and what's the parent of this guy? And then it's base. Okay, because we don't want any other nonsense leaking into this package that would actually start obscuring what the author intended. It said LM is in stats, and stats imports other packages and nothing else, and everyone gets base. Okay, so this way we don't get any bizarre conflicts. But this guy's stats is no longer looking along the search path. In the case of Boost, we saw the search path because Boost's environment was the global environment, and that's chained to the search path. But inside a package, we have much more control, and we don't get all the nonsense of the search path. We get just the things we import. Okay? And that's a good thing, really good thing, because now I can sort of say, I don't care what packages you had attached to your search path. The LM function knows only to look inside the stats package, what the stats package imports, and base. And I think if we actually go back and take a look at this, we can say, okay, and that's all it sees. That's what the LM function can see, other than what's in the stats package. It can see its brothers and sisters in the stats package, and it can see the things it imported, which are from the graphics, and the graphics devices and stuff like that, but nothing else. So it's a very curtailed list. Okay, everyone happy? Why don't we take 10 minutes? Come back in just before whatever it is, just before 7 minutes to 2, and then we'll. Okay. You wanted to ask me a question?
Oh, well, actual question. I was just going to ask you about
Yes. Did you think that they shouldn't get them as catalogs, individual catalogs? I thought you were going to reorganize all the images as catalogs.
Oh, did I promise to do that? I don't remember. I think it would be so.
Oh.
I can.
It doesn't bother me too much. As you can tell, my homeworks are like, go do it. No. Okay, because then the parent environment of that is, and so forth. Okay, they're all chained together. But there's two different. There's the call stack, and then there's going over this direction are these parent frames of the environment, parent environments of the functions, and so forth. We have this non-standard evaluation that's happening because of the formula, and a formula has an environment, and every environment has a parent environment, and so forth, so we know where to find things. So what our problem was the WTS in this boost function. When we did this command, this WTS was getting passed down as the name, not the value of WTS, but as the name WTS. And then in the LM function, we were then going and finding the variable name WTS by looking inside this thing, which was getting passed down as a legitimate data frame by value. And then we were looking inside the data frame for WTS, not finding it there, and then moving on to the environment of the formula, which I said was actually being passed into here and therefore had the global environment as its environment for that formula. And then we were searching in there, and we found WTS in the global workspace. We need to fix that. So I told you enough how to fix it. There's two ways that I can think of easily, but one is a good way and one is a bad way. Okay, so the good way is in this, or let's just call it a better way. Okay. Same code. Put the WTS as a variable inside the data frame. Now WTS will get found inside here, and it's the right WTS, and everything will just go swimmingly. Okay? And that's fine. So we read the documentation. Haha, that was a help. Okay? We probably wouldn't have understood the documentation, so it wasn't really help. Okay, it does help to know this. Okay, what's going on? But this is the thing. But sticking the data in here, sticking the weights into the data frame means that this non-standard evaluation will behave the way it's documented, and off we go. You have to understand that this LM function had to tell us how the weights thing was going to be interpreted. And it did, but it's a little cryptic. There's another way to do this, which is this way. And this is bad. This is not a good way of doing it. This says, take away the model. Don't let me specify the model. I'll specify it in the function. The function is now hard coding the model. Okay? It just says the model is here. Now, what is the environment of this formula? The function. No. An environment cannot be a function. An environment is a place where we have variable names and values. A function is something you invoke. So I'm going to be pedantic. I'm going to be pedantic here. Okay, it's going to be the function call. A function call is a call to a function. So that's be even more pedantic, but you could function call environment, which I call the call frame. So you have only two choices. Once we get down into this, it's either the environment of the function or it's the call frame for this particular call. Okay, so we called boost. We called boost, so we got a call frame for boost, and it had data in this case and steps. Okay, and then, so like we did argument matching and so forth. Then we said model equal, so it creates a new variable down here, which is not a parameter, but it's model, and then it evaluates the formula, so it now gets the formula here. So there's our formula. And because this formula is defined inside this call to boost, this box, which is an environment, which is a call frame, okay, call frame is equivalent to an environment. That is the environment of this formula. So now, the weights are not in the data. I didn't put them in here in this case. So when we pass down to LM, this WTS gets passed down as the name WTS. It then looks inside the data, doesn't find it. But then it says, I will look in the environment of the formula, which is the call frame, which it finds it right here. Okay? And it gets the right thing. Okay? But this sucks because we can only fit one model. Okay? So the other trick we could do is I could do this. If I wanted to, I could do this, and you can tell me what's wrong with this. So this is, let's copy this file. I'm sorry, let's do this. Let's copy boost to boost -1. This is really bad. Okay, mine's bad, okay. Okay, and then we can do this, which is, here's another thing we could say is, we could do something like this, which is environment of the model is equal to sys.frame. Okay, if you don't know what sys.frame is, don't worry about it. It's this call frame. And now I've engineered this, okay? What's wrong with this? I'm basically saying, hey, I'm going to change the environment of the model because the person probably got it wrong. I wanted to find weights here. So, and now this, trust me, sys.frame will give me the current call frame, so it will now do exactly what I did in the last example. What could possibly go wrong? So the person types cylinder plus log weight, which they created earlier. Going back to my example, what could possibly go wrong?
And weights is in the
I put it in my narrative, by the way. This is just so much fun. I was talking about all this stuff. We're talking about the weights for the model, okay, on each observation, and we're talking about the weight of a car here. This weight and the weights over here have nothing to do with each other whatsoever, okay? It just happens to be an unfortunate coincidence. This log weight is a variable that I put in my global variable. This no longer can see the global variable, the global environment, which means it won't find this thing. We'll get a different error message. So all we're saying is this one will now work as long as the model refers to variables that are in here and only in the data. Otherwise, we're out to lunch here, okay? And even worse, if they could, in theory, actually refer to some variable here, and they would get picked up in the wrong place. Oh God, this is really bad news. Okay, so this is just, don't do this. Okay, so the right trick is probably is just to do this, is to actually stick the weights in here, and then they will be found in the environment because of this guy. So,
can't you pass on these weights for the model? And you actually pass the values of the WGS?
No. No, unless you rewrite LM, which we have a volunteer. No, unfortunately, no, you can't. And it wouldn't actually be very hard to rewrite LM to do this, but but there's a reason why it does this, okay? Because basically, when we get down into here, W gets that guy. That's the magic trick here. And if you go back up here, this MF is this weird thing that goes on, and there's non-standard evaluation going on. There's a reason why it does this. No, there is no way, as LM currently stands, to pass down the actual values. You only pass, because of non-standard evaluation, you look as if you're passing down the values, but you're actually passing down the name, which will be used to go off and look for the values in some other weird place that you weren't anticipating. So it's really, truly weird. Okay, yep.
Wouldn't it be slightly more efficient to just create the formula in the same place where you create weights?
Well, it would be really efficient, but it'd be wrong. But other than that, that'd be great. Because remember, Boost is creating the weights. You're creating, the person calling Boost is creating the formula.
So you add like a variable like formula 1 equals the model or everything.
So this is the thing that we.
And you created it in the same environment.
Well, unfortunately, this is one of those. So we had. So your question was this: what if we do? Boost 0.75? Okay, so this, we could do something like this, which is, we can do it inside the for loop or outside. We could basically say model 2 equals model. Okay, and that will work? She said capital.
No, I said that wouldn't work.
Yeah, okay, good. No, this will not work at all, because what I'm doing is I'm making a copy of model, but when you copy the model, you're getting a copy of the model, which means you're copying the environment. The environment isn't changing. The environment is still the original environment of the model you passed in. So it's still going to be the global environment. And this is the problem with designing the software. You want the person, the caller, to be able to specify the model, but we're going to compute the weights.
So if you made some slight change to it, right, then what would the environment be? If you say you change it from a character to a string to a formula, would its environment then be the?
No, we passed in a formula. We did not pass in the
so if you change it so that you were passing in, like, say, a string, and then you're also modifying it when you copied it.
If you were passing in a string, you could do that, where you just type something, but then you have to parse it, and then you have to control where it's getting parsed and what environment is going on to it. But now you've changed the language. You're no longer actually, so error messages will now come in a very weird form, because you get an error in your model string. Well, it's just passed down as a string. Okay, so this is not, it's not, you can get around this in a variety of different ways, but they're not good software practices. So this is a real problem. If we go back over to here and actually look at this guy here, what could possibly go wrong with this approach? Let me just explain to you. Let me just suggest something that could go wrong. MPG is modeled as weights. Suppose I have a variable called weights in my data frame. It's gone. I've just changed it. Okay, so we could call it .wts. We could go .wts, and we just come up with weird names, and somebody will use those weird names in their model. Okay, so this is a real problem of namespace and collisions with variables here because of things. So that's why non-standard evaluation really doesn't work very well. Any questions? Thoughts? So let me just quickly do this. I wrote some other stuff here, which I'm not going to go through very much. So one of the things was this. I'm going to skip ahead. So we were talking about this idea here. If we go back to Michaela's code from Wednesday about this idea. We had a matrix and an R beta, and I was basically saying, you know what? It's a good idea that if we could actually make, this is a very simple example, intentionally simple example, so that we don't see a lot of code. But if this function is computing random, it's generating random numbers. So it's sampling from a distribution, arranging it into a matrix, and then it's actually going through and computing different statistics for each row. If this was more complicated, we'd actually want to separate these two steps out into two different functions, okay? And I would actually like to be able to say, I want to generate these in a different way. So let's imagine that this thing is actually way more complicated than just sampling a bunch of values and arranging them into a matrix. Let's suppose it's doing some sort of time series generation, it's doing all sorts of wacky stuff, and doing post-processing to actually put them into the right, standardizing them, scaling them, doing all sorts of weird things. So we don't want to repeat this code over and over again. The only bit that we actually want to change potentially, so we want to have, so I'm going to just sort of say, let's separate this out. So if you're moving quickly, okay? So what I'd like to be able to say is separate this into two functions, simulate the data, simulate the results. Okay, and then next I'd like to be able to say, you know what, now let's assume this function is extremely complicated. Okay, but it's going to create a matrix with 10 lines of code that actually, after we get the values, we have to do a lot of post-processing. So what I would like to be able to do is avoid copying this 10 lines of code to handle an exponential distribution, and another one for a normal distribution, and another one for any other distribution that you care to name, okay? Because we want to be able to change our beta to being our norm, and we want to change the shape 1 and shape 2 to be the mean and the standard deviation. Or we want to be able to, even worse, we want to be able to generate from an R exponential distribution, Rx, which only takes one parameter. Okay, because then we can do the simulation and see how it changes with the different distributions on the inside. Okay, so we could call it this way. So one of the ways we might actually do this is the following. And again, this is just for writing functions, which there's good ways to write functions and there's less good ways. Okay, so we're going to just adapt this function. Okay, this is one way of doing it that I like to use quite a lot. Is I'm not actually going to compute the values in here. I'm going to put them in up here. I'm going to put them in as a default value is the code I had before, but I'm going to allow the caller to specify the values. Okay, that means I can, if I want, I can just call our norm with this many observations. Okay, and mu is 10 and standard deviation is 4. Okay, and then the rest of the code will stay exactly the same. Is that clear to people? Okay, so you don't have to. You can call it exactly the same way as you used to be able to. Nothing's changed, but I have left a different entry point to be able to override how the values are computed. This is a very useful thing, okay, in many regards. Another example I have is you're writing code to read a 1,000,000-line file, and it's complicated, and you have to read all the lines, and you have to filter some out, and you have to then do pattern matching on the different lines to make the data frame. I'm not running this code every single time on a 1,000,000-line file. What I want to do is actually I want to read 10 lines of this file and hit that, keep passing it back those 10 lines. But I want the function to be able to read the entire file, but I don't want it to do it every time. I want to be able to control what it reads. So what I often do is I'll say, read data, here's the name of a file. By the way, the text or the contents is equal to read lines of file. 2 arguments here just to make myself clear. Okay, which is, so I would do something like this: read equals function. Here's the file name, and by the way, here's the text equals read lines, which just reads the entire text of the file and gets a character vector back. So now I can actually call this as read of abc.txt, but what I can also do is something like the following, which is read lines of abc.txt, okay, and just read the first 10 lines, please, not the 12 billion lines, okay. And now I just call this, now I can just call read of that thing. Okay, so I'm able to control what it sees and override what it actually does by default, but the default still does exactly the right thing. If this isn't clear why this is that this is doing something slightly different and easier to debug and also much more controllable. What happens if it wasn't a file? What happens if I actually just got the data off the web? I could just put them in here and it wouldn't use read lines, okay, or it wouldn't use this thing. Or what happens if they're coming in some other form? I can control this. Now, what's wrong with this function? What can I improve in this function? This is more flexible because I can change the mechanism to generate the sample values. I get to choose R norm. So I would say R norm of n is 1,000. I'd say 1,000 times I, whatever I is 23 times 16, okay, equals, and then I change these because it's no longer a beta distribution. How can I clean this up? There's
Still arguments from the beta,
where?
like alpha and beta are still separate arguments that I want to remove.
Except for I like them because then I don't have to, because they're used here in the default value of this. So I'm loath to get rid of them because they make my life easy. But we'll try to deal with that in a second.
Maybe the 16 to 9.
Yeah, remember what we said about whenever you see a hard-coded number that just looks bad. So I was clever enough to actually change this to, because it was hard-coded in the earlier version as 16. So that should be a parameter. So, okay, put it in here, but then I forgot to use it over here. Like, oh, even worse. Now we're actually getting radically different things. So now I say, oh, change the number of participants to be 10. Then it gives me a warning message about, you got too many things. Or you go, oh, even worse if you say change it to be 32, and then it just starts repeating all the data twice. And you go like, oh, that's weird. So, so you do want to actually fix that up. Okay. What's really annoying though is if I actually want to call this with R norm, I actually have to say call sim data with 24. I don't have to specify these because we're going to ignore them. I say, I leave the 1,000, okay? And then I have to say, oh, an R norm of, okay, 24 times 1,000 times 16. Because it doesn't know, because I'm not in the function, I'm outside the function, and I don't know what I and num participants are, because I'm not using the default code. Is that clear? I'm going quickly, so just asking. So how am I going to fix that? I don't like repeating myself because I make mistakes. I made a mistake here of actually not using the value this variable for this. It's just going to be very, very easy for me to type 24 here, R norm of 22, comma, times 1,000 times 16 or 15 or whatever it is. So that's not good, okay? So I could call it like this. I can also, by the way, just do this. It's great. But remember, this one I made a mistake in. This is 1,000 times 10. Okay, the 10 is here, but I left the 16 out. So this will actually repeat itself over and over again 16 times. So that's not actually good. So, okay, so this is missing the 16. So easy to make a mistake. So what we actually want to do is we want to specify, we don't want to specify this when we're generating the values. Okay, and we also would like to get rid of the alpha and beta because it's just confusing. I'm reading this going like, why do I need alpha and beta? Do I need to read the documentation? We didn't like to read the LM documentation, so why are you confusing me? So here's another way of doing this. Okay, again, I'm moving quickly just in terms of, and I'm going to get to something which I haven't written here yet because I ran out of time, but we'll just do it interactively, but it comes back to scoping. But again, it's good to know how to think about writing functions so that they're as flexible as possible and how you can customize them in the calls. So it's the same thing. It's I, it's n, it's the number of participants. And all I'm saying is you can specify the function to use to generate the random numbers. By default, it'll be R beta, okay? But you can give me any extra arguments that I will pass to R beta. So this just basically says values equals R gen, which is this function, which could be R beta, R norm, R exponential, whatever it is. We'll compute the actual number that you need. That's I times n times this. And we'll pass down any additional arguments you want that you give us. So this will pass down shape equals 1 and shape 2 equals 3 or whatever, or it'll pass down the exponential of 0.1. We just pass those on, okay, and then we just do the rearrangement. So this is much more flexible, okay, and we documented and saying it doesn't matter. We're not going to have 2 arguments. If your random number generator takes 5 arguments, you have to specify all 5, or you may be able to control 3 of them, but not have to specify all 5. So this is good. And in this case, we call it, this will give us back the default, which is we don't specify our beta, but we specify the 2 shape parameters. Okay, and life is good. And now we're down here. So I haven't actually, here's where we stop, okay? I still have to actually do this. It's an R exponential with 0.1, okay? So it's something, and I could, by the way, if you actually think about this, I could actually write a function. Let's just do this. It takes, here's my other one. It takes a function that takes n, okay, the number of observations, okay, let's call it numobs, okay, and it takes dot, 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 okay? This is my generator. So I could actually use this. I'm going to change the dot, dot, dot in a second. But this is how if we look at what R exponential is, or R gen, it takes the number of observations to generate, and then additional parameters. And my function, sim data, will just pass down whatever I pass to it. It will pass them down to this function. Here's what I want to do, okay? I'm going to do something, okay, this is my data, and I'm going to simulate this because I'm not going to bother reading it from somewhere, but imagine this comes out of a CSV file or something. My data is equal to R norm of, okay, 1,000, okay, so it's just, okay, it's boring data, okay, it's fixed. What I want to do is I want to generate a sample from this data. Okay, I want to bootstrap. Okay, I want to actually generate different samples from this empirical distribution. Well, what I can actually do is I can do something like this, which is data values. I'm just going to, okay, and basically what do? I just basically say sample of data values. How many do I want? Numobs, and I'm going to do replace equals true. And now I can use that generator. I can use this generator in my call, can't I? I can say sim data, what did I want? I want 24. Okay, that's my sample size, 1,000 replications, 16 participants. What is it? It's my generator. And by the way, here's my data. Okay, and that's the same thing. Is this clear what's going on? So I'm actually able to write functions now that can actually sample not in a computation, not using a formula, but actually using empirical data, because I'm able to pass down my data. It sees it as a parameter, just like the mean or the shape, but I'm just using it to, it doesn't matter, it's an R object, and I'm using it to actually sample from those values. Everyone happy? I'd like to do one more thing. What I'd really like to do is I'd like not to have to specify this my data. Why? Because I need to pass down 15 different arguments, and I do this all over the place. And I want this function to be self-contained. I would like it to know what its own data are. So here's what I'm going to do. And if you get this, great. And if you don't, ask a question. Okay? I'm going to actually call this generator. Okay? It's a function, and it takes in the data values. Okay? Actually, I'm going to do it this way. What is it? My data. Okay. Well, I'll call it data. I'll call it values. Okay. And what does it do? Start thinking. That's my function. Okay. What's noticeable about that? What's weird about this function? It's a function inside of a function. Okay. So let me just do this. Okay. Let me just go off and grab these numbers. I'll just for fun. Okay. Okay. Here we go. There's my silly data, okay? Now I'm going to go down to this generator function. I'm going to source this in. Okay, so there's a generator. That is a generator. Okay, I'm going to call it with my data, and I'm going to call this rsim. Okay, everyone with me? If you're not, questions, always good. Rsim is what?
Sample of
Sample? Who said? Function? Those two aren't the same thing. Do you want to take it outside? This is how we solve things. It's a function. It's not a sample yet. It's waiting to be. In fact, it will make multiple samples. It is a function from which I can sample many times. Okay? So rsim of 10, I'm not going to give it anything else. Okay? Ta-da! Okay, going to give it rsim 10, ta-da! It's a different set each time because it's truly random. Okay, coming out, and it's sampling from that 1,000 vector, the vector of 1,000 numbers that I gave it in the first place. And if you watch this, if I'm going to now say rsim2 equals, but this one is going to be much more boring. It's going to be from 1 through 10. And now I'm going to say rsim2, which is a function, therefore I can call it, and I'm going to say, give me 3 things. There we go. Give me another 3 things. And it's going to be randomly generated. These two functions look the same. Rsim is that. Rsim2 is the same thing. Okay? What's different? I'll tell you one thing. The environments are the different, and we just spent a heck of a long time talking about how annoying environments are, but they're actually really useful. This environment, remember the environment of the formula was the call frame in which it was constructed, or in the global environment. It was the environment in which the formula was defined. The functions environment, when I define a function like, what is it called, generator, that was at the top level prompt, so its environment is the global environment. But rsim2 has an environment which is the call frame to the call generator in which that thing was returned. And this guy was, we made one call to generator to get rsim, we made a different call to generator to get rsim2, and they have their own environments. And lo and behold, inside both of those environments are all the variables that were defined when this function came into existence, this particular function, which means they both can see values, but values is different in each because they're to 2 different call frames. And these are what are called closures. They basically grab everything that they can see at the time and hold on to their environment, and then we can actually wander our way around and refer to variables in that code without having to pass them in as separate arguments. Is this clear? It's essentially encapsulating some state and then saying we can see that and we can remember that, and we can actually have the same function that behaves differently because they actually see different current values. Now watch this. I'm going to have another guy down here, which is this. It's a function, and I'm going to make this, I'm going to say make counter. Okay, make a counter. Okay, and we're going to say it starts at n is equal to 0. Okay, and it's going to return a function, okay, which is actually going to return 2 functions, okay, which is update. All right, well, we'll say tick. Okay, and it's going to go n gets n plus 1. And we're going to get value equals function that returns n. This is exactly the same. It's a function in which we define 2 other functions. That's good, so it's going to be the same thing. This function will be able to see n. This function will be able to see n. But because they can both see n, this one can change it, and this one will see the updates. R doesn't work this way, okay? You can't change a value from within a function. Unless you use this, and that's global variables. But this isn't a global variable, it's changing this n, not the one in the global environment. So watch this. This is handy, and if you get this, and you're feeling good about yourself, I'm going to go back to the non-standard evaluation, and we're going to do it all over again. Okay, I'll give you a nastier one. This is make counter. Okay, so I'm going to just do this. This is counter 1, and here's counter 2. So K1 tick is a function because it's a list. There it is. Okay, tick, tick, tick. K1 value is 3 because this has changed that counter. But what's K2 value? Nobody's changed its little environment. Nobody's been there yet. But if I do K2 tick, now it's 1. These are 2 functions that have their own state that not only do they remember the inputs, but they can actually change the inputs, which is really, really, really handy. Okay, and we use this in different places. One of the places I use it a lot is in a package called call counter. Okay, when you're profiling code to make it go faster, I mentioned this on Monday, you actually want to know how many times was that function called. Not how long did it take, we'll calculate that one way, but I want to know how many times it was called. So what I'll actually do is I will trace. Remember, trace is a function. I say, trace this function and do this thing every time it gets called. So I say trace, but I give it this counter, which is K1 tick. Call that, and it just counts. Each time it increments the count, and then at the end I say, give me the counts for everything. And the call counter package illustrates this this notion. Okay. Any questions? That was scoping. Okay, that is scoping works just beautifully. You don't use it at all. Okay, but this just walks its way back up into its environment. And you can always ask for the environment. Yes.
Why aren't you using the curly brackets on the functions within the function?
Because there's only one line. Because there's only one expression. This here, I could if you want, but makes you happy?
Necessary
if there's only one expression, you don't need the curly braces because it's obvious when we parse function, we go, oh, there's no curly brace, so the end of this expression will mark the end of the body of the function. But it never hurts you to put the curly braces in. But you can get away with it if there's only one expression, okay? And that includes if your function is if this else that, that's actually only one expression, and it knows. But you don't need the curly braces, and it just makes it slightly less annoying to actually look at, okay? And formats differently. But they're semantically identical. Any other questions on this? I'll give you your money's worth, or else you can all leave. I can go home. There was one other thing I wanted to show you, and that is this. Okay, that's in the OOP directory. So this, again, I'm big into writing functions properly. We're going very quickly. I'm more than happy to write down more of this. If you think this is of value and you want to learn more, let me know and I will write more down. If you want to learn less, I can't help you. Okay. Okay. This is an example of, okay, this is just an example of some code, and this is the way, I'm just using this again. Don't worry about the details. We're doing optical character recognition. What does that mean? You take an image and you want to get back all the text and its location. It's X, Y, width, and height. The confidence, the predictive confidence of that between 0 and 100, okay, and the text values. I want a data frame back, that's fine. We don't even care too much about what we get back for this example. But we're working on an image, okay? So what I actually want to do, so there's a package called our Tesseract, okay, and we can do this, and if you install our Tesseract, which means you have to install Tesseract, okay, and all that sort of stuff, but okay. But you can say system.file of images here, package. Remember what we talked about on Monday? I need a portable way to find a file of data. System.file does this without me having to say C:/users/Duncan TL or whatever it is. My script now is totally independent of what machine we're on. It's portable. Okay, that's great. And then basically we just call get boxes with the image. And there's a couple of arguments, additional arguments. I need to be able to say whether do I want to find characters, or do I want to find words, or do I want to find lines, or do I want to find paragraphs? That's a control thing I have. I want to be able to control whether or not I get back a matrix. I want to get control whether I get back the confidence, or do I want to bother wasting memory on that? Anyway, what this does is it actually comes back with the following. B will actually will have this class. I always ask, whenever I call a function, I want to know what class is the result. We had a debate whether my generator function returned a sample or the function. So we just asked, said, what is it? It's the class of. This one is unusual. For most people, you may not have seen this. The class is just a character vector, so it's regular character vector, but it's got two classes. We recognize this one, we don't recognize this one. Okay, that's okay. Doesn't matter. The class is a character vector as long as you want it to be. Okay, everything has a class. You can't not have a class. Even if you have a class, you'll basically have an empty string at the very worst. But everything has. So we have the names of the data frame, because this is really a data frame. It tells us it's a data frame, and the names are just the names of the columns, and life is fine. So this is good. So what I haven't told you about is, I said we pass it an image. It performs the OCR and returns a data frame. What's an image? A matrix is a matrix. So, okay, so we have a matrix. Pardon?
Could be 1, could be 3.
A matrix, it could be, what could be 1 and 3, sorry?
There could be 1. There could be more than 1 matrix image.
So it could be, it's typically going to be a 2-dimensional image at least, because otherwise it's just like just a row of pixels. It's like not particular, hardly an image. So it could be this, or it could actually be a 3-dimensional, 3D. Oh, this would be an array. In R, this would be an array. This would be a matrix. Okay, what else could it be? What else? What are the different ways we could talk about an image?
Raster.
Could be raster. Okay, so we can talk about raster, so that we'd like to be able to handle that too. Anything else? Raster. What's a raster? It's a raster.
Histology.
It really is. It's a particular way of representing an image. Okay, so don't worry about it. Okay, it's actually in this world, because it just is. It's actually a thing called. We can also have it as a pix for a pic map. Okay, that's because this is talking to C code. So we can actually, it's stored in memory, okay, but we do actually want these for various reasons. This is just a different way of ingesting an image into this system, and then I can mess with it, because I don't ever really want to bring it into R. I want to play with it in C code that knows how to do nice things to it, so that's useful. What else is it? There's one obvious way to refer to an image. In fact, I did it up there. It's just a file name. Okay, it just sits on a disk, and that's all. Okay, so we want this. We want to be able to say, give me a file name, and I'll treat it as a file name. Give me a pix, which means that I've already read it in, I pre-processed it, converted, turned it into black and white, removed lines, cropped it, and done all sorts of wacky things before R ever really saw it. But I need to get it to the OCR engine, the optical character recognition engine. I want to be able to handle a raster image, which is a different file format, okay? When I say file here, this is actually a PNG, a JPEG, a TIFF file. Oh my God, there's different types of, but for us, we don't care about this. This is actually a file name. That's just a character vector, although we could actually we could say it's not just an arbitrary string, it's a file name. It actually corresponds to a path. So we're giving it more conceptual information. But we could also have a matrix. We could also, so the array, there's a package called the PNG package, and in there's a thing called read PNG, and this will come back with a 3-dimensional array, okay, so stacks of matrices. So this is all we would like to be able to handle all of this. Now, in fact, actually, what we'd like to also be able to do is there is a mechanism in this package. And again, this is very specific to this package. Don't worry about the details, but because I'm trying to get at actually how we're going to write clever functions that simplify the complexity of the different types of inputs. For image, we have 1, 2, 3, 4, 5 different types of ways of representing an image, and I want my function to be able to handle all 5 of those, which means I'm going to have a lot of if statements. If the class of this is a character vector, then treat it as a file name. If it's a pick object, treat it as this. Okay, and then that's going to be a combinatorial explosion of code, and it's going to be really ugly and messy. And the whole point of this is, how do I write clean code that is extensible, so that when I add a 6th way of writing an image, I never change the existing code. That's a magical trick if you can do it, because it says I don't have to test the original code. I haven't changed it, it still behaves the same way, but my functions will still work for this and actually handle the 6th case simply. And even better still is if I can now actually do something in the 6th code that is simpler to write because it uses code from the other 5. That would be great news too. Well, that's what we're going to do here. Okay, so I'm going to just pick 3 of those because that's all I thought of when I was writing this down this morning. Okay, and this is down here. Okay, so we have a file name, a pre-processed image object, which is my PIX, my PIX, and a tesseract engine object. The reason I want that is we have an OCR engine. It's got, I kid you not, 670 different options you can set. Okay, and I want to set those once, and I want to run it on multiple images. I do not want to have to set those 670 options each time. Okay, it takes time, it takes some code to do that, so that's fine. So I want to be able to, I also want to be able to control this. This is what my function might look like. GetBox is a function that takes some object, okay, which is one of these 3 different types. It tells me the level, which is it a word? Do I want to work at the character, the word, the line, or the paragraph level? If you have any criticism of this, by the way, of this code, start yelling, okay? Keep confidences true, because I do want the confidences, but by default I can turn it off because sometimes I just couldn't care less. Just give me the answers back. Okay, do I want a matrix or a data frame? Because I may want to change the structure, and I don't want to go to the trouble of making a data frame and then turning it into a matrix later on, because there's actually 2 or 3 commands to do that, because it's not simple. I can't just use as.matrix because I'll have the text in there. I need to, and then all the x, y coordinates will become characters. So I'd actually, what I want is arrange the data differently. Give me back the x, the y's, and the widths and the heights, and put the text in as the row names. Whereas the data frame, I'll just do it then as columns. So I want to be able to control that. That's nice. You don't need to do that, but it's kind of nice. Might as well. It doesn't cost us much. But look what I'm going to do. I'm going to say if the object is a character, so inherits from the class character, then go ahead and treat it as a file name, and then there's 20 lines of code to do that. But if it's a PIX, well, there's 19 different commands to do that. So this is mushrooming into a huge, big block of code. Now, what's even worse is this has 20 lines, let's say, of code. This one has 19 lines of code, but they share 12. So I'm going to start doing some gymnastics to try to avoid repeating myself. So I'm going to make more if statements. If it's either of these, do these first 12 lines and then skip, and I'll do the if statement again, okay, for one of them, and then I'll continue on. This is not, pardon?
Why don't you just copy it?
I don't want to copy it because remember what I said? The second you copy it, somebody inserts a bug. Okay, this is the computer is watching you copy it and then says, I'm going to change the code. Okay? It does, I tell you. Okay, so copying is bad news. So one thing we can do is we can actually try to abstract out the 12 common lines into another function. We'll do that. That's what we talked about before. You try to avoid repeating yourself because it's a nightmare to read. It's a nightmare to maintain. Okay. If it's only 1 line, who cares? 2 lines, beginning to care. 3 lines, it's over. Okay. This is what so there's a much better way of doing this. Okay. What if we did something like, you could actually put the onus on the user. Okay. I've got to remember where we did this. Okay, you could put the onus on the user, which is, we could just come up with better names. We could actually split that one big function into getBoxes.character, getBoxes.pick, getBoxes.tesseract API, and each of them is now a single function. There's no if statement. The user just actually has to say getBoxes.character, not getBoxes. They have to know what object they're dealing with, and then remember that you called it getBoxes.pick or something like that. And they got to know that it's not getBoxes.dataframe, but it's getBoxes of OCR results or something like that. So, but you could easily come up with this naming convention or any other naming convention. You could put underscores in here. You could use different camel case patterns or whatever it is. But the nice thing is, this is a reasonably obvious one. It just is annoying for the poor user that they have to constantly add in the class name. And then if they ever change it from being a matrix to a data frame, they have to change all the code that actually calls stuff. So this is kind of not as valuable as possible. But here's your trick. Go ahead and write those functions. You write those functions because you're implementing these three, what we call methods. And then you write a generic function. And you've seen this before because we actually saw this on Monday. You write getBoxes, and you say, and has exactly the same definition as the big ugly one we were going to write. But all it does is say, go find the method for getBoxes. And what this magically does is it says, I'm going to take the class of object. Okay, so it's going to be character. Okay, it's going to take character, and then it's going to look for getBoxes.character. And if it finds a function called getBoxes.character, it uses it and says, I'm done. It calls that function. If it doesn't find getBoxes.character, it looks for getBoxes.default. And if it finds that, it calls that, and we're done. And if it doesn't find getBoxes.default, it says, you're an idiot. Okay, I can't do this. I have no default method. Okay, and then so we just write this here, and all it does is it says, hey, if you're given a file name, okay, and I happen to know this because about the R Tesseract package, go and create one of these Tesseract engines and tell it what file to process. Oh, and then just call getBoxes. Hang on a second, that's a bit magical. Okay, well, there's a little bit we have to add into this as well, which is, okay, but that should be actually Tesseract API, should be. Here's cut and paste problems. Okay, so this now says, here's a method for one of these Tesseract objects. Now, this does all the heavy lifting, okay? The other one was easy. It just says, go make something that we can pass on to another method for getBoxes. This goes ahead and calls the C code, gets the actual boxes for all the things. Then it goes through and keeps the confidences. It turns it into a matrix or a data frame. Does all this goofy stuff that we have to do, but then it just returns the answer. Okay? And this again is, this should be a pick. This is what happens when you do this on the train. Okay? This one says, create a Tesseract object. Don't give it an image name. Don't do anything. Just give me an empty engine. Now set the image, because this is for a this is for an image that I read into C code through C code. Okay, now set the image again. That we have to have a function to do this, but now it says now go compute the boxes. I've set this engine up with all the necessary information to just go and actually call the Tesseract API, the previous method I just wrote. So these methods are actually now very easy to write because we're writing them in terms of other derived methods. Everyone with me on this? That you basically can now actually split these functions out based on the types of the inputs. We can actually make this much cleaner. So you don't need all these if statements. You just actually can just actually have different methods that are automatically invoked by a generic function, which is the use method. Okay, so we had getBoxes that said just go find the method. That's all I do. R will take care of finding the method, and we can now split these functions out, which makes it much easier to maintain and test. What's the other benefit? How do I handle a raster? So suppose we are a matrix, let's say, or an array. So now, how do I handle these other types? We had 6 types, okay, or 5 types, and I handled 3 of them. But now somebody comes along and says, I do know what a raster image is, so I want to use this on a raster image. So how do I actually add that?
It's just a new method for the raster image.
It's just a new method. So what I will do is something like, I will go off and I will say something like get boxes dot raster. Or if we do it for an array, okay, and what I'd probably do in this case, and again, we have to have the underlying functionality for it, but the key point is, what I'm going to do is I'm going to copy that in, and I'm going to basically say the following, which is, I'm going to basically say something like this: turn that array into a pix object. Okay? Which just says, just if you know, and we have to actually put that in, but this is a much better way of doing it, which says take the array, turn it into a pix object, and then just go on and do the same thing, okay? Which means, and then we don't have to write any extra code, but the beauty of this is you decided to add a function to handle an array. I didn't. I wrote this code, and I put it in an R package, and you then begged me, you sent an email to me begging me to actually handle an array, and I said, nah, I don't want to. I don't want to maintain your stupid code. Okay, just do it. So then somebody else sent me another email saying, "Can you actually add functions for a raster?" And I go like, no. Okay. So then you both decided to fork my package, and each of you added your own method, and now there's 2 packages, and they don't do the right thing. So somebody who wants to use both has to use 2 packages. Okay, this is ugly. So we actually want to centralize all the code. But the point is, okay, but the point is, I refused to actually to add this gratuitously, but you can actually have this in your own R session. Okay, you can have another R package that just loads my package and that just provides this. And so you're not copying my package. You're just adding new functionality to my package when it's loaded, and this is great. Okay, so this is a very, very neat way of actually just separating out the concerns instead of one huge function with a bunch of if statements, which cannot be changed except for by the owner of the package. If you want to add an array into that, you have to take my code, change my code, and send it back to me. This way, you could just send me this back, and I'd say, sure, it doesn't touch my code. I don't have to test anything. I just add this nonsense in. Or I can say, I don't even have to add it in. You just use it and distribute it yourself. So this is a much more extensible way, just basically being able to allow people to slide in additions to handle other types. There's just one, each method is now separated, but the user only has to say get boxes. There's one verb, it just, what happens just works for the user. Does anyone know of a function like this in R? Something like summary, plot this matrix, sure, plot this vector, sure, and they all behave totally differently, okay, because they look at it and say, I got a matrix, I got a vector, I've got a data frame, I've got an LM object, I will plot them in totally different ways, okay, so if you actually, so, yes?
I'm just kind of confused how...
Yep.
How is actually, what if the thing that you're trying to input can't be converted into a fix?
Then it will fail, and you'll get an error, and that's absolutely fine. So now it's up to me to actually, it's also up to me to, that was the way I implemented this. I implemented it this way just because I'm moving quickly for one. I said, by the way, this is a very nice way to do it. I could have sort of said, I could have written this quite happily as, I could have actually, let's call this pix here. I could have also just written this as, convert array to pix, okay? And there it is, and I get my pix objects, and then I have to go off and write that function, okay? So I could write this function. My other way of doing it is actually a very nice mechanism, but if you don't write that function, if you cannot find a way to get your array into a pix object, you're dead.
Which is outsourcing if statements to functions.
That's all we're doing is actually just delegating them into different places. Now, what I do like, and then you're having these support functions, but for the user, it's a lot easier. There's one function they call. For the maintainers, and for the maintainer, the if statements are now all gone. And what's even better is that I can extend it. I can add somebody else. You can come along and add your own methods, and they don't conflict with mine. I don't have to test yours or anything like that, but they still exist for everybody else. So you literally have enhanced matters. What I really do like is I use this a lot, which is I like to write functions that just basically say as an array turns into a pix. There's a particular way it's written down below as to how you actually construct this, okay? Because I like to say, all I want to do is convert this object into the right format and then hand it off. And then my code becomes extremely easy to read, very easy to write, and life is good. Okay, but no, you still have to write code. I'm sorry, I wish there was an answer for that. Okay, but in many cases, you've broken the problem into a smaller problem. You're saying convert it to something that I know how to solve the problem for, and that's good. Okay, so this is one thing. Okay, what about this? Did you notice I told you that the result was an OCR result and a data frame, okay? So what actually happens is the following. Remember what I said? When I got B, which I said, get me the boxes, and I assigned the result to B, and the class actually is OCR results and data frame. Now, if you actually go back and look at my code, there it is. That's the magic trick. How do we make an object a particular class? You just say, hey, the class of you is this, and shut up and just keep this around, okay? You can make anything into a class, a particular class, by just assigning a character vector to that. And by the way, if you make a mistake and just, like I did, OCR lowercase results, that's a whole different ballgame. R doesn't check. Just like that's your mistake, okay? But that's fine. You just set the thing. Now, the nice thing about this is I can actually have plot OCR results. I can actually define a new method for plot. Just say plot.ocr results, and this now draws a nice picture of the image with my results in the right places. So I can actually see the results separately from the image. Okay, it's a data frame, so this thing still acts as a data frame. I can go in and get the X and the Y, the width and the height, and all the columns. I can subset it, which I still want. So I want it to be two things. I want it to be a data frame, and I want it to be a special object that knows how to plot. So we wrote a little plot.ocr results, which means you can do the following, okay? You can take my code that does this, and all you do is you say, get boxes, okay? And you just say, oh, by the way, change the class to be my OCR results. It also is OCR results, and it's also data frame. And now the nice thing about it is, okay, now the nice thing about it is you can provide your own plot.myOCR results. So you can provide a customized version of this, still using all of the other code. And again, and by the way, what you can basically say is, I want the plot to behave in a particular way for my OCR results, differently from this. But I want everything to behave like a data frame for everything else, like the square bracket. So I want all of that stuff to inherit. So you can introduce a new class that says, but I want everything to be inherited from each of these two classes, so I don't have to write code for every single operation, but I can customize for particular operations or particular generic functions. Okay, this is actually a very simple mechanism for actually writing good, clean code that is extensible by you and maintainable by you, where you don't have to retest code every time you make a change, because you're not changing each function, you're just adding new methods. And the beauty is you're leaving the door open for everybody else to add to it as well, which this is what we call object-oriented programming, okay, in a particular way, and it's extensible. Basically, people can extend your work and inherit from your work. The stuff we actually were looking at down here, I like to call, when we were doing this sim data, this I like to call that is actually, it's customizable rather than extensible. You can literally just change the parameters. And this behaves totally differently, but it still has the same structure. Here, it's intended that you're leaving the door open for people to change things. The other one is that the structure can actually be layered on top of, which is Very simple, and it's well worth, if you're writing this yourself, it's so easy to introduce a new class. Just put a class equal, you say class of the result is equal to OCR results and data frame. And then you can go off and write your own plot method, your own summarize method. So do you know any code that works this way? Plot is one. Anything else? All of the modeling software, all of the LM, GLM, and all that sort of stuff works on this S3 class mechanism. It's a ridiculous class. If you show this to a computer scientist, they think this is a hilarious joke that anyone could actually write software like this, because it is so unstructured. I can do this if I like. I told you that an OCR result is a data frame that's actually got XY coordinates and so forth, but I can just say this, x equals 1, class of x equals OCR results, and it's a data frame, and it's a Bob too. Okay, okay. R couldn't care less. Okay, R just has no concerns. You're a grown adult who can make proclamations. So it seems extraordinarily brittle and fragile, but it's amazing people can actually make this work. Okay, and with a tiny bit of sort of discipline, lots of people can actually add to this sort of stuff. So it's a very, very simple mechanism. I'll say all I need to do now is say plot. I say summarize. So summary, you see, is a use method. So I say summary.ocr results is a function that takes object dot dot dot. And I'm going to just return, it returns pi. It's a stupid thing, but okay. But now I say summary of x, I get back pi. Okay, that's how easy it is to write a method and how to introduce a brand new class or OCR results, because in this case we haven't actually defined that yet. So it's easy to do this. There is a method, if you don't like the fact that this is extremely brittle, so I can actually have two objects. This should be a data frame, but it's not. I've just declared it to be a data frame. I'm lying, okay, but I haven't got hurt yet, okay. But if you want it to be more structured, you can actually use what's called S4, where you can actually say set class, and I'm going to say it's an OCR results, okay, and it's going to be, it contains a data frame. And I can put constraints on it that it has to have 5 columns, and each column has to be a numeric vector. So we can go into actually structured code if we want for writing full-fledged software. But the S3 stuff works remarkably well. And again, it simplifies writing code, and it simplifies maintaining code, and it's extensible, and that's a huge win if you're going to build on your own code, literally just for yourself, where you're literally just making your life easier later on. You can do this. Any questions? Because I can go home. Any questions or any thoughts about anything or unrelated to what I've spoken about? Yes.
What is the advantage of extending the summary with a new method compared to having a function called summary OCR and making evident that is for this type of?
Do you really want to? Do you want to type plot.lm, plot.glm, plot.matrix? Do you want? I mean, or do you want to just type plot and have R know what to do?
It depends on the situation.
For the most part, we actually want to think in terms of a single. We want because the nice thing about that, as I mentioned, because if you have, so if you do the following, so if you do the following, okay, why, okay, okay. So if you write code like this, it's a function. It takes a function, okay, x, okay, and you say, well, x is a data frame, so you're going to say plot.data.frame of x, okay. We're going to do that. Then we're going to do lm.data frame of x, okay, and you get your fit back, and then you're going to say plot.lm of fit, okay, and now you say it's a matrix. I'm going to have to change that to be dot matrix. I'm going to change GLM, and I'm therefore going to have to change this. So I'm constantly changing code. Okay, whereas the beauty of if I actually just write this in terms of the generics, okay, which is now, this is LM. I don't have to worry about if it's a matrix or not. It takes care of it for me. It's that, and it's that. And now that code remains invariant and will actually work for a data frame, for my data frame, for my OCR results, which is also a data frame. This code remains unchanged, which means I don't have to test it again. Testing code is a pain in the butt, okay, because it breaks. So every time you touch it, it breaks. And you have to, or more to the point, you have to worry about it breaking. So this is actually a much more, this gains you a lot because that a large body of code doesn't change. It is possible, of course, if you pass in some nonsense to it, that it will break, that it will fail. But then you just have to add a tiny little method for it, hopefully a small method. Okay, does that make sense? So it does, and again, the holy grail for people who write software, whether they be software developers or just writing software for your own purposes, is laziness. We love laziness, which is, I don't want to go back and test that code. I don't want to change it, and if I change it, I have to test it. And that's the most boring part of software development. Any other questions or thoughts? I'm going to say I'm more than happy to try to answer any questions whatsoever. It would, yes.
When you say standard evaluation, what exactly are you referring to, like base R first?
I'm saying that
it's all relative to the R language. It's not in a larger sense of
no.
program.
No, every programming language changes, it decides how things are going to work. Okay, and basically what we're talking about in this case is scope and how arguments are evaluated, and all I'm saying is, like, in that world, when we looked at the LM early on, the first thing we did here, we said we're calling LM and we say weights equals WTS. That WTS behaved totally differently from the data argument, where we actually passed it down from the caller. And the other one was, no, we went off and looked around it, but that is totally R's own world. Yes, and I mean, and literally, you know, I mean, if you want, I mean, you just to be clear about this, we saw it again. We saw it, but I can do the following: E is equal to a new environment. Okay, $X is equal to 10. Okay, X is equal to 0. Okay, and now what I'm actually going to do is, what am I going to do here is. If I say eval quote X, okay, I get 0. Yes, everyone happy? And now if I do this, I get 10. So that same expression behaves totally differently just when I slide something else in, and you don't know what's going on, and that's bad. No other language does this. That's not true, but this is incredibly powerful and incredibly easy to abuse. Okay, we do. And as you see, the LM function does this, and it thinks it's clever.
If we want to understand that a little bit better, what is a good place to understand those basics? There's some notes that I put up from the R fundamentals workshop that I did before, and I've written it down a little bit. Whether that's the best place or is one thing. The book Advanced R by Hadley Wickham is a good place for describing that reasonably succinctly. There's another place it's described, which I'm not suggesting is actually the most readable form, and that is in the R language definition that comes with every version of R. And as one of the authors of that said, I'm not going for readability, just correctness. And we said, we know. It's like unreadable. So, you know, it's there, but the Advanced R is probably the simplest, but it's actually not very hard. There's not very much to it. It is, if you understand these call frames and the parent environments, that's the magic. I have a picture of it somewhere on the R fundamentals again, it's easy for me to say, oh, it's obvious. By the way, it's not. And anyway, it is just somebody decided that this is the way it looks, the way it should work. If you do, when I say no other language does this, lots of other languages have started doing it actually. But it dates back to
other languages like Lisp and so forth, where you actually have this notion of closures, and and you actually get into this theory called lambda calculus, where it's actually everything makes perfect sense, and for functional programming, it's also very natural. So there are other places to, if you want to totally abstract it, you don't want to do that. Just it's unreadable. If you think the R language definition is unreadable, boy, lambda calculus and all that sort of stuff is far too abstract. But there are nice concepts of these things.
Have they had his reasons to break the rules? Or is it
As some people have said, it's more intuitive. There's consistency. At the same time, when he was doing that, he made some things slightly faster, because you might as well when you're taking the opportunity. He also sort of said, well, we don't need some cases like that. So it's all. There's, again, it's not that it's valuable, but there's a cost to it, which is now you have to program with two different models. And I hope what I got across today is, and the very first example with LM is, my God, if you don't understand what's happening, you can get yourself into serious problems. And the best you can actually hope for is an error, because if you get answers back, you could be toast. You could be looking really stupid. But no, it makes sense. And so we also have these things called DSLs, domain specific languages, and this nice thing, which is basically that's what these are. Okay, they're basically saying, oh, for this particular purpose, we'll just do it this particular way. And it's really nice when we have domain specific languages like regular expressions, where you say grep, and you say, I want to find everything that starts with A through G, followed by followed by 4, but it can actually be an optional 4, okay, or XYZ, and okay, so we do that, and we go like, okay, that's a weird language. Okay, thank you very much. It's a very powerful language, but the good thing about this is no one is saying that R is going to interpret that. It's in strings, and we hand it straight off to somebody else. So it's clear that you can't mistake it for R. Okay, not that you could. Okay, and that's you can elevate these up into domain-specific languages, and I've done it myself. I do it. I mean, we do it for fun, and we also do it for utility. But but now you've got to decide whether or not you can actually handle reasoning about two languages. Most people can, apparently, until it doesn't work. And then there's an issue. But it's fine. Whatever works for you. Honestly, I'm not saying don't. I'm just saying be aware that there is a cost. And when you go to stand up and defend your thesis and somebody says, I think you're wrong, you better be careful, okay? Because if you are, that's a very crushing experience, which is, okay, well, thank you. I'll go back to my thesis. Anything else? Yes.
So why is LM design so used as standard evaluation?
The reason, I believe, I'm pretty certain it's in the documentation. I'm lucky I have a sense of history about these things. The good news is, so this is actually one of those situations where it is debatable as to whether this is a good thing, but so the S language doesn't have environment, and it has a different scoping mechanism. So the S language came well before R, but the S language defined LM and all these good things, and R came to be like S, but it had this extra power, so people started experimenting with it in interesting ways. When you do something like this, in LM, you can basically say, let me just be clear, you can say something like this. You can say LM of MPG is modeled against weight. And then you can say my data is MT cars, but by the way, I would like the subset to be equal to all the ones for the MPG is greater than 20. Okay? And I'd like the weights to be equal to rep 1 through this is, let's just do it this way, uniform 32, okay? So this is, okay, so I'm making up random weights, which is, again, don't do this statistically, okay? Okay, so now the nice thing about this is, what it will actually do is it will go through and say, okay, fine, this subset argument is kind of useful, kind of actually not necessary, but it's inherited. What this does is, we didn't have to say MT cars $MPG.
It just knows to actually do it in the context of this and this. When it's filtered this, we now end up with, let's say, 10 observations left in our data set, which means we have to go back and filter the weights too. So it's doing this all in exactly the same uniform manner. That's why it's deciding to do this, as far as I can tell. Okay, I think that's the motivation, is that this is now all consistent with the subset and the weights. Otherwise, you hand in the weights, you'd still be left with 32 weights when you've only got 10 observations. So everything gets done consistently. This is a design decision as to which is the most useful default to have. I personally wouldn't have done it this way. I would have said, if you want to subset your data, just subset your data ahead of time. How hard is that? Okay. Well, it is hard, because if this has got 12 variables, you have to say empty cars, $MPG, empty cars, $weight, something else, something else. Again, it doesn't bother me. I like to be right rather than hopeful that everything's going to, but that's the logic of this, is that everything then becomes uniform. And if you actually take a look, as I was saying, this is a bizarre piece of code in some regards. This goes off and says, okay, what it does is it says match all of the arguments in the call to the definition of LM. Now, okay, so we match this call, and now we say, now we basically say, go get that and match these guys. So we only look at a subset of the parameter, the arguments in this call. Okay, if we say, keep the call to LM, then match where we found these arguments in this call. This function is looking back up and saying, how was I called? Now go and actually pull out a small piece of this as a language object, and then it says, replace, where is it saying this now? Basically, it says replace, where are we? I was looking at this before. Yes, it says replace the call to LM with a call to model.frame, and then call that. This is saving code. Okay, this is actually literally inspecting its own call and emulating that call to be exactly the same. No matter how this particular call was made, I'm going to repeat that as a call to model.frame. It could have quite happily actually written this a different way, but it didn't. And then it goes down and says, okay, now I've got this, and now go off and get my model weights from this MF object, which I've messed around with. I'm going to call that again. So it's a really terse, nice way of writing code that no one can understand. Apparently I need to update my so it's kind of weird. So it's people, these are the things people like me do, and they for fun, but it's not necessarily helpful. So it's kind of wacky. Anything else? I'm going home. I'm getting my train. I'm getting my train. I'd say the whole part of a big premise of this was actually that it really is useful to actually learn how to do this thing, so it gets out of the way, that you don't have to worry about whether it's right or wrong, that you write good software for your own benefit and potentially for other people. It's not hard. This is all a man-made system, and I say that very explicitly, it is man-made. There isn't a single woman in our core, which is a really bad thing. Okay, very, very bad thing. But it's not hard to actually write good code. It just takes a little bit of practice, but it is not like some people say, I can't do math. I don't intuit math. This thing is designed to be understood, okay, and to be usable. It's not supposed to be trivial. It's just, but there are better practices, and if you want to learn more about them, do so, okay? Come and talk to me more, talk to each other, and then do code review, okay? I'm happy to talk to people. We also have this DSI affiliates program where many of you are already here because you're doing interdisciplinary or your work, or you're actually learning that you have to learn other skills that were not part of your curriculum. The easiest way to do that is to actually do it with other people rather than actually learning it all by yourselves. The psychology group, who's well represented here, they have each other. But many other people are in programs by themselves. If nothing else, look up and down the programs programs in terms of your years. If you're a third year, there's probably somebody in fifth year or first year who wants to learn this. Not this, but lots of different things that are not in your curriculum. But hanging out in the DSI is time consuming, but that's unfortunately how you learn stuff that is not in your curriculum. It's nice when there's a course that teaches you everything you need, but there's so much stuff that you have to learn these days. God, I'm glad I'm not a student anymore. You know. And by the way, speaking of which, there's one little thing I meant to mention, and that was this, which is okay. And that was this. Remember, we created a data set. Remember, we said you can use system.file. And you can put stuff in a portable place, and people use system.file to find that file. But if it's a CSV file, we sort of say, well, then they still have to read .csv, and then they have to convert the columns into whatever format it was supposed to be. They could easily get the character encoding wrong. There's lots of ways to go wrong. So we said it's much nicer if you actually are, if you want an R object, put it in the data directory, okay? And then it just gets loaded directly. You say data of empty cars, it just comes in with all the right formatting, all the right processing done already. And what I basically said is the way you create these is, you take your CSV file, you start up an R session, and you type the command that the user should type, and then you say save of that object into a file name. So here's just something this is an example of something that none of you need to know. It's very useful. This is what we use in software all over the place. And it's what I use when I'm writing a book or when I'm writing a paper. I use the same mechanism, which has nothing to do with an R package. But that's this thing called a make file. How many of you know what make is? Okay, not many, okay? And that's fine. What this is a weird little thing, and it's another language all unto itself. This is the magic. If you ever wanted to use this in the context of a data directory, suppose I have 100 CSV files, okay? And I want to just create an RDA file so people can just say data of data 1, data 2, data 3, or whatever it is. Well, what I need to do is I need to issue this command, read.csv of file 1, strings as factors, convert the stuff, okay? And then I need to just say save it as an RDS, or just save in this particular case. Okay, it should be save. Okay, so the trouble is, then somebody changes the CSV file. Should you rerun this command? Yes, because the other one's out of date. You got 100 of them. How do you know which ones to update? You do them all, and it takes 3 hours, okay, or whatever it is. This thing is very nice. You're basically saying this RDA file depends on this CSV file. If this one has a timestamp that is more recent than this one, then I need to execute this command. Otherwise, it's fine. So you just say make, and it goes, oh, that one, that one, that one, and then we're done. Okay, and it just executes, it brings everything up to date. What's really nice is if this thing depends on this thing, and this thing depends on this thing, and then this thing depends on this thing, it will scan and figure out the entire graph of dependencies and only update the minimal amount that it needs to. So we use this in software all the time because we're compiling code that all has to get glued together. We make a change in one file. There's no way I'm going to compile all of R again. It just goes through and says, you only changed one file, I'll just make this one little change. But then that trickles into building another thing that builds one more thing, and then it's very, very fast. So the make is an actual dependency, a program that handles dependencies for you. And you can basically make these rules that say, here's how you make an RDA file from a CSV file. Just do it for me, but only do the minimum amount of work. Again, laziness is good. So, will you ever find this taught in a class? No. Is it useful? Yes, for those of you who use LaTeX, for example, to actually write your thesis, okay? Well, you're probably going to end up with 100 files, one for each chapter, one for each section within a chapter. Does the PDF that I'm going to give to grad studies actually represent the last version, or just the last time I make this PDF? It really better be the right one, okay? And you just say make. It's even worse if you say, hey, does the plot I have in my paper correspond to the latest run of my code, or did I change the code and forget to run the code to make that plot again. It's happened a lot of times. We go, "Ooh, I didn't mean that. I didn't mean that." Somebody actually just did that recently, which they actually submitted the old version of a paper, and it was told, "We've already reviewed this one," and they go, "Oh, sorry, here you go," you know, and that's embarrassing. Okay, so something that actually automates stuff for you is very, very useful. Why would you know about this? Because you hang out with people who teach you things that aren't in your curriculum. Okay, and there's an enormous amount of things that may save you time, maybe not. It's a crapshoot. Anyway, if you have any questions, we'll take this.
What's an RDS file?
An RDS file. It's an R data serialized file. It's called serialization. We serialize to disk and then we deserialize back into memory. Okay, but an RDS file is different from an RDA file because an RDS file saves. So if I have something like the following, hopefully this will make it clear. If I have something like the following, I say x is equal to 1 through 10, okay? And if I say save RDS x into a file called bob.rds, you can call it any name you want, okay? It says, sure, no problem, okay? Now, if I do this, if I say read RDS of bob.rds, well, let me get rid of x. Read of RDS gives me back the answer. It gives me back the value that I saved. It takes the contents of x and writes them to a disk. When I read it back in again, I get the content. There is no recollection of x whatsoever. Okay, so if I take a look at x here, it doesn't exist. If I do the following, if I say the following, x equals 1 through 10, now I'm making it again. I say save x. And you might think this is annoying because I say file equals bob.rda now, okay? Now I remove x, and now I say load bob.rda. This is different, okay? This just says, sure. Okay, thanks very much. And now I say x, and it says, I restored the value back to the original name that you gave it, which is really bad news. I have this big X that I just spent hours computing, and then I load, you send me an RDA file, and I load it, and hey, you just overwrote my data. Okay, so that's really bad news. You can arrange to have it go somewhere else. But this actually restores the values back to their variables. The RDS file just returns the contents, nothing to do with the variables. And the reason we need both is because x equals 1 to 10, y is equal to 20 through 40, okay? And now I say save x, y, file equals bob.rda. Now, remove x and y, okay? And this time I'm actually going to do the following. E is equal to a new.env, okay? And now I'm going to say load of bob.rda, and I'm going to say into E, because I want it to be sane. Okay, it says sure, no problem. Okay, and now I say what's in E? It's got X and Y again, so it's restored multiple objects right back. So we use this when you quit R and it says do you want to save, and you say yes, it just dumps everything in your workspace into a .r data file and then restores it later on when you come along. Okay, and so the RDA is the values and the variable names. The RDS file is just the value of one object and one object alone, because you can't. But it could be a list with 2 objects, but it's still one object which has many other objects. Does that answer your question? I like RDS files. I like single objects because that means if I have terabytes of data and I want to go in and get just a little piece, you know, I have 4 objects and each of them is a terabyte, and I want to get at the 3rd one. Why do I need to load the whole stupid thing? There are ways around it, but it's not worth it. Yep.
Is the make file thing you were talking about, is that part of R?
No.
It's part of your, it comes with your attractive operating system. Okay, okay, well, it comes with code tools when you actually do that. It's beautiful. It is independent of R. That's why I can use it for LaTeX. I can use it to actually, I can use it to do all sorts of different things to keep things up to date with, by just writing rules. But we use it in R all over the place, build R and to build R packages and so forth. But the nice thing is that it is a system that you can use then in Python and in C code and C++ code and in LaTeX.
That you run from the shell, or?
Typically, yes, but then you can do that from R or Python too. So you can invoke it from anywhere, but yes, so it's a different language. And then this is the nice thing, is when you learn concepts that are language independent, or that apply to multiple languages, this is handy. Yeah. And I say, I mean, and then there's another thing which we didn't get into, which is, I'm just mentioning it, which is this again, just because I happen to be thinking about it. This is, and again, this is way advanced, but not very complicated, as Jane will attest, which is this. This is actually what we do when we're actually writing, when R will do this if you install it from source, but even for R packages, we basically say, hey, I need to know about your operating system that you're trying to install. I need to know about your machine on which I'm trying to install this software. So we write software to probe your machine and then customize the package to enable certain functionality or disable certain functionality or control things. So this is actually configuring a package or a piece of software for your machine and your machine alone in an optimal way. And we actually, there is a little language, a domain-specific language for actually helping to write these configuration scripts to actually probe your machine. Anything else? Good. I'm out of here. I'm going to make the train. I can make the train in 25 minutes. Thank you, guys.